Hi, everyone. Welcome back to Dave's Math Channel. I'm your host, David Tear, and this is my seventh and final video in a series on complex numbers. And this is on Euler's formula, which is considered by many mathematicians to be, the most important or the most amazing formula in mathematics. It's a really amazing formula, and I'll show it to you on this slide. So here's what it says. It says e to the I phi is equal to cosine phi plus I sine phi. I was using theta most of the time. You can use whatever variable you want, but phi is supposed to be an angle, and it's usually a real number, although it doesn't have to be real. Turns out it can be imaginary as well. This formula holds for all z, as a matter of fact. Some people write it as e to the I z equals cosine z plus I sine z. Uh, the proof of this formula, I'm not going to actually prove this formula today because the proof involves calculus. You usually learn the proof in either first or second year calculus. It's not that hard if you know some basic calculus, but since I'm not talking about calculus in this series, I'm not going to actually prove it formally, although I'll give you sort of an intuitive proof. And there's another formula that's considered equally amazing. This is a special case. The formula on the bottom is called Euler's identity. It says e to the I pi plus 1 equals 0. This is very easy to get from Euler's formula. You just plug in pi for theta. And remember that we're using radians here. So if you plug in pi for phi, what do you get? E to the I pi equals cosine pi plus I sine pi. Well, as you know, cosine pi, that's like cosine of 180 degrees. That's -1. And sine pi, that's like sine of 180 degrees. That's 0. So the right side you get for Euler's formula is going to be -1. And so you got e to the I pi equals -1. Well, this is a little bit nicer way to write it. You just add 1 to both sides. You get e to the I pi plus 1 equals 0. Why is this formula so amazing? Well, the reason I think a lot of mathematicians consider this like the most amazing formula in all of mathematics is because it involves five constants, e, I, pi, 1, and 0. These are considered probably the five most important constants in all of mathematics. I mean, 0 and 1 are fundamental. 1 is the unit. That's what we all count with. 0 took a long time to accept the existence of 0, but 0 is the additive identity element. And we can't do without 0, obviously. So 0 and 1, once you have 0, 1, you can sort of build up all the integers additively, at least. And then these three other constants, I've been talking about in this series. I is just the imaginary unit. Pi. Let's do this one first. Pi. You guys all know about pi. Pi is usually considered the most important mathematical constant, and E is probably, I mean, irrational constant. E is probably the second most important. So this is amazing formula. One equation with these five, probably the five most important constants in all mathematics. Actually, a friend of mine told me there's another fact that's really amazing about this formula. It involves also the two most basic arithmetic operations, plus addition, and it also involves exponentiation. So it involves exponentiation, addition, and equality. Kind of the three most basic mathematical operations, as well as the five most basic mathematical constants. I kind of think of this formula as like a unified field theory of mathematics. I mean, the holy grail in physics is to find a theory of everything, a theory that in principle would explain everything there is to know about physics. Well, obviously, this formula, I kind of think of this like a unified field theory of math. It doesn't tell you everything about math, but it has like the five most important numbers in math and the three most basic operations all in one equation. So I don't know if it's really unified field theory, but it's just an amazing equation. I guess I can sort of think of more like Maxwell's equations in physics. Those explain everything there is to know about electricity and magnetism, and you can write them on a T-shirt. Well, this you can easily write on a T-shirt. In fact, you can write this on a pen if you want. You just need one line. So I just think it's a really amazing formula. And I don't know which of these forms is more amazing. They're kind of, I mean, the one on top is a little more useful because you can let phi be anything you want. And this is used all the time in science, by the way, this formula on top. But anyway, that's enough of Euler's formula or his identity. And here's a picture of it. So, we've been working with it. If we work with the unit circle, the circle here is what's called the unit circle in the complex plane. It's just the circle of radius 1 centered at the origin. And this has all the complex numbers along this circle, all the complex numbers whose absolute value is equal to 1. And you can write them all in the form e to the I theta. Here they do use theta instead of phi. And geometrically, you can see that e to the I theta is nothing but cosine theta plus I sine theta. So that's a nice geometric way to visualize e to the I theta. It's just the unit complex number with angle theta, or the complex number, if you like, with absolute value 1 and argument theta. Very nice way to write it. And what else can I say? I said I wasn't going to prove Euler's formula, but this is probably the next best thing. I mean, this you do not need calculus for. Remember, I was defining this thing called cis in the last couple of videos, cis theta. I'm defining that to be cosine theta plus I sine theta because it's just easier to write down. And then let's just look at some properties of cis. You can derive these yourself. I mean, the first formula is probably the hardest to derive. But you can get this one just from the additive identities for cosine and sine. If you work out what cis theta 1 and then plus theta 2 is, it's going to be cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. There's formulas you can use for the additive formulas for cosine and sine, and then you break it up, and you can actually prove that it's equal to cis theta 1 times cis theta 2. It's not a very easy proof, but you don't need calculus for it. And the next two formulas here, the second formula is just de Moivre's formula. I did prove that one for you in the last video. You can prove it pretty easily using induction, or you can, you use induction for this. So, and then the inverse of that one, so n is supposed to be an integer here, a positive integer. And then you can divide by that integer first. So cis of n theta is going to be cis theta to the power n. And cis of theta over n is going to be nth root of cis theta. And there's one last formula we kind of need. Cis of pi, that's easy to do. That's just cosine pi plus I sine pi. And I already did this for you earlier. This is equal to -1. So we have these four properties of cis. Well, something should strike you with these formulas. Cis looks like an exponential function, right? Every exponential function satisfies the first three equations. So we already know that cis of theta has the form of some number k to the power theta. We don't know what k is. K is the base. Or we could equivalently write it as e to the, I don't know, e to the r theta. I don't want to use r. E to the k theta. Usually people use b for the base, so maybe I should say cis of theta is b to the theta for some base b. But we could also write as e to the k theta if we just let b equal e to the k. So we don't know what k is yet. But look at the last equation here. Cis of pi is -1. That means e to the k pi is -1. Well, if you plug in I for k, then this is true. I mean, it's just we know I mean, so k, yeah. What was I trying to say here? E to the k pi. I don't know. I'm getting a little confused now. But what you should know is that e to the I. If we write cis theta equal e to the I theta, then e to the I theta does satisfy all these properties I've written down here. Maybe I didn't prove that k is equal to I. I don't really know how to prove that. Maybe you do need calculus to prove that. But it certainly has a form of an exponential function. And yeah, so anyway, that's kind of an intuitive proof. Maybe I left a few details out. Like I said, you really need calculus to prove Euler's formula in detail, but at least this should convince you that it has the right form. It is an exponential function. The only question is what the base is, what the value of k is. But anyway, and I thought I'd just finish with an interesting example. What if we wanted to calculate I to the I power? It turns out that you can calculate any base to any complex power using this formula. The trick is you write the base as e to the, in this case, I, you can write as e to the I times I pi over 2. Why can you write it that way? Because um, it's just e to the I log, uh, how does that work? B is equal to e to the log b. Oh, yeah, yeah. So I is e to the log I, but log I is nothing but I pi over 2 because log is the inverse. I'm talking about natural log now. ln of I is equal to I pi over 2. That's pretty easy to see because e to the I pi over 2 is I. That just comes from Euler's formula. That means that I pi over 2 is the natural logarithm of I, but you can write I as e to the log natural log I, which is e to the I pi over 2, and we're raising it to the I power. So what you're left with after you do this is e to the I times pi over 2. You can combine the two i's, that gives you I squared, and we know that I squared is -1. So when you're done with this whole calculation, you get e to the minus pi over 2, which is pretty amazing because this is a real number. Who would have thought that when you raise the imaginary unit to the power of the imaginary unit, two imaginary numbers, an imaginary number to its imaginary power, that just happens to be real. And it can actually calculate its value. It's about 0.207879. It's an irrational number. It goes on forever. But I think this is kind of neat. So, and there's a lot more applications of Euler's formula. So anyway, that concludes my video for today. It also concludes my series on complex numbers. So thank you for watching. Long live math, and I'll see you next time.